So far is a story of computing moments of inertia of extended objects by representing R and dm in terms of a variable x. And so we did various linear objects. Here's a typical kind of problem that we might want to solve. Find the moment of inertia of a long thin rod of length L and mass M about a point that is 1/3 the distance from its end. And so at this point we're kind of pros at this. We create for ourselves a representative element. We set our origin at O, and we say that dm is equal to density times dx, which is equal to n over L times dx. And therefore, the moment of inertia about point O will be an integral from negative L over 3 to positive 2L over 3 of r radius squared times and this is like the third or fourth computation like this that we've done, and so we're starting to see the patterns that happen. So we have 2L over 3. Here's my factor of a third. Cubed minus negative L over 3 cubed. And we get 8 over 27 all cubed plus another 1 over 27 all cubed. So that when the dust settles, we get 9 over 27 L cubed. 9 over 27, of course, is 1/3. Factors of L cancel. We're kind of used to these things now, and we get 1/9 in L squared. And if you observe the different results that we had, remember that when we took the moment of inertia about its end, we got 1/3 in L squared. When we did the moment of inertia about the center, we got 1/12 in L squared. And now when we did the moment of inertia about a point 1/3 of the way from the end, we got 1/9 in L squared. And it occurs to us that maybe all that's going to happen as we shift our axis of revolution is that we're going to change the coefficient out. And that actually turns out to be the case, and it also turns out that tomorrow we'll have an efficient tool for shifting that axis of revolution. We call it the parallel axis theorem, so that we don't have to walk through the entire integration process. So what we'd like to do now is to extend this idea to take a look at objects in 2 dimensions. And I want to begin with the whole family of objects that are circular. Pose the problem like this. Find the moment of inertia about point O for a solid disk of radius r, mass m, and uniform density. Radius r, mass m, and of uniform density. Now, to understand what we're talking about, solid disks could be anything ranging from a compact diskette to a soup can that is being rolled down an inclined plane, to a, let's see here, What other kinds of disc-like objects might we have? About a tire, if that tire is square-ish. So the height of that tire is actually in material here, the thickness of it, because we can take that entire disk and essentially compress it so that it is two-dimensional, all the mass is contained right here. So our point O is like this, and our axis of revolution is coming out, and we are rotating around this axis of revolution with radius r. So our plan is once again to integrate r squared dm, and to do this, our differential elements that we're going to take are going to be differential elements that are at a constant radius from the axis of revolution. In other words, we're going to take circular strips and add them up. And the reason that we're going to do this, we draw this a little bit more carefully. So, this is our point axis of revolution right here. If I consider all of the points on this thin circular strip right here, every single one of these points has exactly the same radius r from the axis of revolution. Now I made my strip too thick.
What is the difference?
Here. That, I'm sorry? So the idea is that we're going to take our disk, we're going to use a mathematical knife to cut it into thin cylindrical shells. Shades of easy calculus yesterday, right? And each one of these shells has a thickness of dr, and each one is at an average radius r. And the point is that by using this as my differential element dm right here, by using that as my differential element dm, what I've done is to find the set of all points that is at a constant radius r. So my representative element consists of all of the points that are at a fixed radius r. And what I can do now is to essentially integrate outwards from 0 to big R, and I will get the total moment of inertia. So it would look like this. dm is going to be equal to density times the area of my differential element. And here I'm using area because I've got a two-dimensional object. Now what is that density? That density is equal to the mass divided by the total area of the disk. And what is the differential element of area? Well, because this is really, really thin, what I'm going to do is to simply slit it and unroll it. And when I slit it and unroll it, what I get is a really long, thin rectangle. So here is my dm unrolled, and the thickness of that rectangle is dr, and the length of that rectangle is the circumference of the circle, 2 pi r. It is eerie and utterly coincidental that BC Calc students did this exact thing yesterday. Does that make sense to everybody? Now notice that big R here is the radius of the circle, and it is a constant to this problem. Whereas the little r here is the radius of my differential element, and it is variable. As r changes from 0 out to big R, then this circumference will also change. This is the radius of the differential element. So now I'm ready to set up the moment of inertia about O as the integral of r squared dm. And I can construct that as r squared times this whole expression. Big M over pi big R squared times 2 pi little r is the r. And my limits of integration are going to be from the very first radius, which is 0, out to the very last radius, which is big R. Well, there's a whole lot of mathematical carnage that can happen. First of all, the pi's cancel. Second of all, constants come to the outside. Let's identify them. We've got a 2, we've got a big M, and we've got a big R squared. And what's left is little r squared times r times dr, or little r cubed dr. So that we get r to the 4th over 0 to big R, which gives me, over 4, sorry, which gives me 1/2 of m big R to the 4th divided by big R squared, or 1/2 of m R squared.
And if you're this hallway here, you're from the chemistry lab, and then we have two.
Now what's, go ahead and leave it open actually.
There's something wrong with that.
Yeah. So what's interesting about this result is the comparisons what the, to a system of discrete particles. If instead I had had a single point mass of big M at a radius of r, then my moment of inertia about 0.0 would have been mr squared. Here I get 1/2 of mr squared. Why is that? Well, it's because what I did was I took this mass right here and I now distributed it inwards toward the radius, so that some of my mass m is closer to the axis than radius r, and as a result, our moment of inertia is lower.
Good old point math.
Good old point mass.
So the height of the object is known.
That's right. The height of the object doesn't matter, and here's why. The object is rotating about this axis right here. Let me try to draw this for Josh's sake. So let's do a sort of extended object. That, and our object is going to be like so. And it's going to be rotating about an axis through its center. Here and here. It's going to go around like that. When it goes around like that, all of the points, if I take my mathematical knife and slice like this, all the way down, like so that my dm is a cylindrical shelf like that, all of the points along this length right here are all at the same radius. So they're all going to go around together. And as a result of that, each one of these points along right here, when I add them up, throw them into the integral, and add them up, they're going to contribute the same amount. So the length of that object really doesn't matter. Now, it indirectly matters because if I make my object longer, then probably my mass goes up, right? So you see the effect of the length indirectly in the mass, but in terms of distribution, okay? Now, I'd like to consider a similar problem, and that is find the moment of inertia of a hollow disk of outer radius R2 and inner radius R1 with mass M, and again with uniform density. Moments of inertia. About the center. Now, just to understand what we're talking about here, what we're looking at is a disk that is filled in over here. And it has an inner radius R1, and all of the points inside here are empty space. And then it has an outer radius R2. Now, if we compare this problem to the disk problem, then you can see that this is going to be very similar. It makes sense that I'm going to use the same integration strategy. I'm going to choose a DM that is a circular shell right here. The difference is, well, there are a couple of differences. The first difference is that I am not going to start integrating at 0, but instead I'm going to start integrating at R1. I can start integrating at 0, but if I do, I get a bunch of zeros, so there's no point. The second difference is that all of the mass that I had that was distributed in towards the center is now shoved towards the outside, so that I expect that my result is going to be larger. In other words, what I'm not doing is I'm not taking the circular disk of mass M and cutting out part of it, because then I would lose mass M. Instead, what I'm doing is basically taking and pushing that mass M towards the outside. So let's go ahead and construct our moment of inertia using the same logic that we did before. We're going to start by identifying the set of all points that is at a constant distance from the origin. And here's our set of points like this. And let me do it in a different color so that it's spiffy. Green. And we'll make this at a distance of R. So that dm is equal to density plus dA, or m over, now the area is tricky. What is the area of my region right here? Big R minus small r?
R2 minus
2
R.
Yes, it is the area of the entire circular region. Take away the area of the entire whole. Now, I know I said earlier that we are not just cutting out mass, and that's true, but in terms of geometrical area, the area of this region is found by taking the area of the big circle and subtracting out the area of the small circle. So I'm not subtracting radii. Now, what about the dA? Well, dA is the same logic that we had before. The dA is simply the area of this differential strip, which is going to be equal to circumference times thickness. And now, I0 equals the integral of r squared dm, which is the integral from R1 to R2 of little r squared times this big ugly constant. I think we can see that there's a common factor of pi that cancels. Oh, I threw my 2 into the wrong place. Like that. Out come the constants. And what's left behind is delightfully simple. It's the integral of r cubed dr. Mhm. So that, I get this guy right here, and I get r to the fourth over 4, r1 to r2, which gives me now a really interesting relationship where we have one factor of 2 canceling, so that I get m over 2 r2 squared minus r1 squared times r2 to the fourth minus r1. Yeah, that looks really horrible as a result. However, it can be simplified by observing that we have a difference of squares factoring pattern going on right here. In the numerator, we have r2 squared squared minus r1 squared squared. So that if I factor it, pulling out my 1/2 m, something really delightful happens. And that is I get r2 squared minus r1 squared times r2 squared plus r1 squared. And these factors cancel. So that when the dust settles, I get a result that is not all that bad. Now the addition here is counterintuitive because we want to instinctively we want to visualize it as taking away mass. But we're not taking away mass, we are shoving it towards the outside, which means that we are distributing it further away from the axis. And so therefore it makes sense that our moment of inertia should go up compared to a disk. But do notice that the limit works out. If I take the limit as r1 goes to 0 of our result, then what I get is the moment of inertia of a solid disk, which makes a whole lot of sense. This also suggests that I could continue that process. What I could do is to take the mass and continue to shove it out until all of the mass resides at outer radius R2. And when I do, what I get is a thin hoop. So let's consider now the moment of inertia of a thin hoop of mass m and radius r about its center. An example of a thin hoop might be a hula hoop, for example, where all of the mass is concentrated right at the radius of that hula hoop. So we can actually approach this problem in one of two ways. One way that we could approach it is to integrate r squared dm, and we can do that. But I think an easier way to approach this is to think of the thin hoop as a limiting case of the hollow disk. If I take the expression 1/2 mr squared, mr2 squared plus r1 squared, and I take the limit as r1 approaches r2 of that expression, then what I'm doing visually is to take all of my mass and now shove it all the way out to the outside radius. In other words, I'm getting a thin hoop. And when I do, then I get 2 r2 squared times 1/2, which gives me mr2 squared. Taking this result and applying it to the thin hoop of radius r, we conclude that I0 is equal to mr squared.
Nope.
Is it a noun or a verb? Maybe it's a preposition.
Whatever you want it to be.
Place the pen through the desk. Does this visualization process make sense to you guys? How are you doing, Chloe? You good? Okay. Now, I want to come back and see why this result makes a whole lot of sense. Let's consider integrating r squared dm in this way. If I take a small element of mass dm, like so, then I can evaluate that mass, that dm, by considering that it is a small fraction of the entire circle. So that I can take and write the density of the mass distribution of the hoop as the entire mass divided by the entire arc around the circle, which is 2 pi times the radius of that circular hoop. And I can say therefore that dm is equal to density times a little piece of distance around the circle, and therefore I0 should be equal to the integral of r squared dm. But for all of the pieces on this circle, the radius is a constant. It is equal to big R. And dm is simply equal to mass over 2 pi r times ds. And the elements of ds are going to be integrated from an arbitrary starting point, let's say 0 right here, all the way around to the last ds is equal to 2 pi r. So that what I get when I pull out the constants are mr squared over 2 pi r times the integral from 0 to 2 pi r of ds, which is equal to mr squared over 2 pi r times 2 pi r. And those all cancel, giving you mr squared. In other words, you want to think of this thin hoop as being made up of a lot of little discrete particles, each of which has a contribution to the moment of inertia of dm times r squared, because that's our basic formula. And now when I add up all the way around, I get the total mass times r squared. Density times, yeah, so here, as I go around like this, because my hoop is really thin, I only have one dimension to consider. Yeah, so I'm not doing it in terms of area, I'm doing it in terms of length. So that's it for our family of circular objects. We basically have a disk and then variations on that disk by having holes of various sizes. Finally, I want to consider a more advanced question, which would be the moment of inertia of a rectangular plate through an axis on its edge. through an axis, well, yeah, let's do rectangular plates. Through axis on the edge, and then also about an axis through the center. So here we have a rectangular plate, and our dimensions for the rectangular plate are going to be A and B. And we're going to first consider an axis of revolution that is about one edge of the plate. So a book here, a good model for a rectangular plate. And so we're first considering the moment of inertia of the book as it revolves about an axis like so. And so we're kind of familiar with how we want to go about this. If we set this as 0, then we're going to take as our DM the set of all points that is at a constant radius from the axis of revolution. And that set of points is going to be a rectangular strip that has a thickness of dx and has a height of b. So we can say that the density of our plate is equal to the total mass of the plate divided by the total area. And we can say that the dm is equal to density times area, differential area, which is equal to m over AB times b dx. And interestingly, the factors of b cancel out. In other words, the length of this b right here doesn't matter. Ooh, I think I know where this is going. So, the integral of r squared dm then is going to be equal to the integral from the first x out to the last x, from 0 to a, of m over a times x squared dx. But that's equal to simply m over a times x cubed over 3 from 0 to a, which is equal to 1/3 ma squared. Wait a second, I've seen a formula that's a whole lot like this before. What was this, the moment of inertia of? Long thin rod, about what point? About the end. Oh! In other words, viewed from the point of view of this axis, all I'm doing is looking at a long thin rod about its end. Why? Because all of these points here are all the same distance away from the axis. So I might as well just collapse them into a single dimension. Aha. So that gives us a really powerful visualization. If my object is homogeneous, essentially in this direction, I can collapse it. But now let's consider same object, really different axis of revolution. Find the moment of inertia of a rectangular plate uniform density mass m, dimensions a by b, about an axis through the center and perpendicular to the plate. Now, this is tricky, and it gets at one of the challenging things about, golly, 3D math, just not my thing.
Oh,
What I'm trying to do is to show that this axis is perpendicular here. Let me just help you visualize it. What we're doing is talking about rotating it this way.
okay.
So we're taking this entire plate and we are revolving that plate in its own plane. I have an axis perpendicular to that plane. The reason this is tricky is that you're going to be tempted to think about this as this revolution right here, about an axis through the middle. That would be 1/12 in a squared.
Yeah.
Right. This is not that. This is about an axis that is completely perpendicular to the plane. And we're going to get a completely different result. And to get this, we need to do a little bit slightly more advanced calculus. I'm going to introduce this idea of integrating over an area. We're going to need it later on when we do Gauss's law. Because I cannot take strips that are all the same distance away from the axis of revolution, I'm going to have to resort to taking small pieces that have a height of dy and a width of dx. And each piece is going to be at an individual distance r away from the center. But if I take my origin to be at the center right here and put axes on this, then each piece that I so describe is going to be at a coordinate of x comma y. So that if I use the Pythagorean theorem, then I get r squared is equal to x squared plus y squared, where x and y are independent variables from each other. So in other words, I can go across here and have a whole bunch of different pieces that have different x's with the same y, or I could go down right here and get a whole bunch of pieces that have the same x but different y's. So x and y are independent of each other. So I can now say, first of all, that the density is equal to the mass over the area. That part's easy. And now the dm is going to be equal to density times the element of area, which is equal to the density times dx times dy. So this is the very first time we've seen this, where we have little tiny pieces whose areas are dx times dy. And now when I integrate, watch how the integration takes place. I'm actually going to have to integrate twice. I'm going to integrate across to add up all the little pieces dx into horizontal strips. And then I'm going to add up those horizontal strips by integrating a second time in the y direction to get the total contribution. So my integral is actually going to be a double integral. I'm going to integrate x squared plus y squared, which is the radius squared of each dm, times density dx dy. And I'm going to integrate from the first x to the last. We read this inside out. So I'm going to integrate from the first x to the last x as I integrate with respect to x. And then I'm going to integrate from the first y to the last y as I integrate with respect to y. It's crazy, but it's cool, isn't it? Yeah. Yes, so we're actually reading this inside out. We're integrating like that. So we're going to integrate with respect to x first, and then we will take the results of that and integrate with respect to y. And the picture is that as I integrate with respect to x, what I'm going to do is to add up lots of these little tiny rectangles. And when I add up lots of little tiny rectangles, I'm going to get a horizontal strip at that point. And I will also get a horizontal strip at this point, a horizontal strip and a horizontal strip, so I get lots of little horizontal strips. And then when I take those and integrate those dy, I will be adding up all the horizontal strips dy in order to get the whole thing. So picture it as basically doing a double scan. We're scanning across first, and then taking those results and scanning up to get the whole thing. Yes?
So when the rectangular plate was like that,
Mm-hmm.
could you have done this?
Yes.
But we just made it easier for ourselves.
We did, and we
Okay.
were justified in doing that because all of the results here were constant,
Right. But now they're all
Yes.
different.
but now they're all at different points away. Okay, now the fun part is because x and y are independent variables, when I integrate with respect to x, y is a constant. As I integrate along this horizontal strip right here, y remains constant. So, I can pull out the m over ab constants all the way to the outside. And when I integrate on the inside here, I get 1/3 x cubed plus y squared x from 0 to a. And the outside integral remains in place. Substituting, this gives me 1/3 a cubed plus ay squared. And what this represents is the moment of inertia contribution of each horizontal strip. As that horizontal strip gets out away from the edge, essentially. Oh, you know what I did? I chose the wrong origin. Look at my limits of integration and take a look at my radius right here. What I accidentally did was I said we were integrating from 0 out to a right here. Oops. Yep. So this actually needs to be negative a over 2 to positive a over 2 in my setup. Boy, I'm sorry about that. That's okay. We can fix it easily enough. And that's going to give us now a slightly different result. That's going to give us, let's see, 2 times 1/3, so it's going to be 1/12 of a cubed plus 2 times 1/2 plus ay squared. Well, let's finish this out. When I integrate 1/12 of a cubed from negative b over 2 to positive b over 2, I get 1/12 a cubed b. And when I integrate y squared from from negative b over 2 to positive b over 2, then I'm going to get 1/12 of b cubed. And this looks really ugly, but I see that I have a common factor of 1/12. And I also have a common factor of AB right here. So that what I'm left with is an interesting and somewhat satisfying result, which is that my moment of inertia is 1/12 m times a squared plus b squared. In other words, this guy acts like a rod of length a squared plus group a squared plus b squared about its center. I can visualize this as being equivalent to this.